Let me tell you about pain. It was originally scheduled for the 4th of November, but I've been told that we can't have a room that evening. So count on sometime in the first week of November having your next midterm. Pain. I will, once I get confirmation about a room, I will let you know. Okay. Did I say pain? Okay, last time we were talking about IIR filtering, infinite impulse response filters. We had this recursive difference equation that we started analyzing. I don't think I got to the block diagram for this. So remember we said from the difference equation you should always be able to get to the block diagram and vice versa. So here we have the block diagram for this equation. You've got the output at any given sample n. It's equal to its delayed version. So this is a unit delay block. Sometimes delay blocks are represented with a z inverse. And the terminology has to do with z transforms, which is a topic in 120. But it doesn't really matter what you call it. A single d is a unit delay block. Z inverse is a unit delay block. Z to the minus m is an m sample delay block. Where m is an integer. So here y of n goes into this delay block. And what the output of that is y of n minus 1. It's essentially a one sample storage element. This is a multiplicative box. So what's out here is alpha times the delayed version of y. And that gets added to the input at sample n. And that's what produces the output at sample n. Sometimes if I don't put anything around this adder block module, you can assume that they're being added together. Sometimes we put a plus on one, minus on another, in which case that would be self-explanatory. You'll know which one is getting subtracted from what. But essentially, this is a delay adder gain block diagram representation for this. Actually, I think that was part B of the exercise I'd given you at the end of the last lecture. Let's review where we were. We had figured out the impulse response for this system from last time. What was the impulse response, for those of you who take notes or have good memories? Zero for less than 0. And then what about non-negative zeros? Alpha to the n. So combining all that information, the impulse response is alpha to the n times the unit step. So the unit step takes care of the 0 values for negative time. And let's say alpha is, I don't know, 3/4. And you have example. Then you have the value 1 at 0, 3/4 at 1, 3/4 squared at 2, and you can see it decays to 0. If alpha is 1, you get the unit step. If alpha is greater than 1, you get a growing one-sided exponential. So what I want to do now is talk about the frequency response to the system. What is the frequency response of this system? You can either start with this, or you can start with that. Did we do this last time, the frequency response? No. That's the problem with teaching 20 and 120 simultaneously. You never know which example I did in in which class. So you studied two ways of figuring out frequency responses last time. One was by starting off with the difference equation, and the other is by plugging the impulse response into the definition. So method one, you have the definition. And method two is you use the difference equation, the linear constant coefficient difference equation, and plug in what? X of n equals e to the I omega n. Okay? So what I want to do is give you a few minutes to try it out using both methods. You can start with whichever one you like. Obviously, you have a choice on an exam as to how you're going to go about this. Make sure that you get to the same answer using both methods. And once you consult your neighbors and have agreed on an answer, then I'll sick meatball on you. The second method? Come again? Okay. So we'll go over the second one. That's what I thought. Yeah, I did put the summation lambda to the n equals 0 to infinity equals 1 over 1 minus lambda for when lambda is strictly less than 1 last time. That's what I thought we did. Okay, so when you, I'll do both of them I'll do both of them quickly since this is going to be a review then. So method 1, we have h of omega. Now the summation goes from where to where? 0 to infinity. And from 0 to infinity, h of n is what? Alpha to the n. U of n is simply 1. And I have e to the minus I omega n. So I bunch these together. So I have 0 to infinity, alpha e to the minus I omega to the n. And now this constitutes my lambda. Okay? I forgot to write this down this time, but last time I mentioned that alpha is inside the unit circle. So if that's the case, then this summation using this closed form will be 1 over 1 minus alpha e to the minus I omega, because the magnitude of this lambda is simply the magnitude of alpha times the magnitude of the complex exponential, and this, you know, is 1. So this is alpha, and we're told that that's less than 1. So we can use the closed form expression. Okay? Method 2, you plug in x of n equals the complex exponential. What would the output be? H of omega e to the I omega n. So looking at the equation, let me write the equation again. Y of n equals alpha y of n minus 1 plus x of n. Again, alpha is less than 1. So h of omega e to the I omega n is on the left-hand side. You have another y of n term here, so you have alpha. What's y of n minus 1? That was totally inaudible. E to the I omega, you got to put an n minus 1. So there's an n, and here's your minus 1. What else? H of omega. Plus e to the I omega n, which is my input. Now what do we do? I heard divide, I heard subtract. Divide by e to the I omega n. This is always on the unit circle, so you're guaranteed that it's never 0. And when you divide and collect all the terms involving h of omega, you get on the left-hand side 1 minus alpha e to the minus I omega, this whole thing, multiplied by h. And on the right-hand side, the only thing that's left is the number 1. And so you get the same frequency response using this method. Let me guess what you're going to ask. You're going to ask, we didn't even use the fact that alpha is less than 1 in this equation. Tell me I'm good. Tell me I'm good. There's an implicit assumption in going through this derivation, and that is that the h of omega, the frequency response, exists, meaning that this infinite summation converges. That's an embedded assumption when you go through this method. So the problem that I usually pose would be figure out the frequency response of this filter. That should give you the idea that, okay, it has a well-defined frequency response. If it does, for this input, you get this output. So, yeah. Otherwise, it's not obvious from this derivation. There's an assumption embedded in there. Very good. There was another hand up here. This is the description of the system. I didn't derive this. I have a system that's described by this difference equation. Yeah. Now let's talk about the frequency response, in particular the magnitude response. So plot h of omega. This is where we start using some geometric reasoning to get a feel for how this filter behaves. A good procedure for this is to convert h of omega to a ratio of polynomials in e to the I omega where the power of each of the e to the I omegas is non-negative. So right now I have an e to the minus I omega sitting in the denominator. I want to get rid of that. So what do? Something more simpler than conjugate.
Look at alpha e to the minus I omega is alpha upon e to the I omega and bring that up.
Bring that up. Okay. So in other words, you multiply the top and bottom by e to the I omega. So if I do that, I get e to the I omega over e to the I omega minus alpha. You with me? The nice thing about this e to the I omega is that you can look at where you are on the unit circle. It's a point on the unit circle, e to the I omega. And this is the unit circle. Okay? When I look at the magnitude of this function, magnitude of a ratio is what? Ratio of the magnitude. So I have the ratio of e to the I omega over the ratio of e to the I omega minus alpha. And what do I have in the numerator? 1. So I have 1 over the magnitude of this quantity. Now suppose alpha is here. Alpha in general is somewhere in the unit circle. Let's just say alpha is real, and it's over here. Alpha. And what are we picked 3/4 there, so let's pick 3/4 here. Okay? Every complex number has a vector representation on the complex plane. We did this a while ago. So if you were to draw a vector corresponding to e to the I omega minus alpha, what would it be? Raise your hand. Why don't you try it? Your name is? Brian. Brian. So
the vector going in the same direction from e to the I omega down to alpha.
So Brian says it's a vector between these two. Where's the arrow? Where's the arrow?
The arrow's on the alpha axis.
Are you sure? Dissenting views? So the arrow always goes on the one that doesn't have the negative sign on it. So the arrow goes here. And if you are ever in doubt, draw the vector for e to the I omega. That's here. That's the vector. Okay? That's e to the I omega. Draw the vector for alpha. So minus alpha will be that. And what's the... Wait a minute. E to the I omega. Is that right? Yeah. So, yeah, exactly. So now you draw the parallelogram. and that's e to the I omega minus alpha, okay, which is parallel to that. So that vector, so e to the I omega takes the arrowhead, the other one takes the tail. So it's the red vector that you're interested in. I'll redraw this figure to remove the clutter. So here's what we have. We have the unit circle. We have e to the I omega. We have alpha. And we have a vector from alpha to e to the I omega. So this is alpha. And this vector is e to the I omega minus alpha. So as omega changes, e to the I omega, you can think of it as a particle. It goes around this unit circle. And as it goes around the unit circle, the magnitude response is the inverse of the magnitude of this red vector. Are you here? Are you here? Thank you. So, when is the magnitude response at its peak value? When the red vector is what? Smallest. The red vector has the magnitude that's in the denominator. So when the denominator is the smallest, that's when h of omega magnitude is the largest. Where does that happen on the unit circle? At 0. So now I'm plotting. I'm going to plot from minus pi to pi. So at 0, I know I'm at peak. And what is the peak value? What is the length of this red vector when omega equals 0? 1 minus alpha, which in our example is 1/4. Oh, wait. No. That's the length of the red vector. So what's the magnitude? 1 over that. So it's 4 over 3. No, 4. I can't do arithmetic, man. 4. Okay? When is the magnitude response the smallest? For what value of omega? Pi. When omega comes, when e to the I omega comes here, that's when the length of the red vector is the longest. And that occurs at pi or minus pi. And what is the value when you're there? What's the length of the vector? 1 plus alpha. And 1 over that is 1 over 1 plus alpha. And for our case, what is that number? 1 plus alpha, 1 plus 3/4? 7 4/7. So it turns out, now, to get the concavity, you just plot a few points and you get the concavity right. But the basic idea is to recognize that this filter favors lower frequencies, and this favors the highest frequencies. Everything is symmetric about 0, so that's how you get the fact that this plot, which I have not drawn to be symmetric, is symmetric. What kind of filter is this? Low-pass filter. You had a question? No, omega can go negative. I can take omega negative. Alpha is positive.
So on a test, if you wanted to graph it, we would have to give it the value.
That's right. That's right. So in fact, I'm going through this kind of an analysis to show you ways of perturbing this problem to change this filter into a different type of filter. What would I have? What's the easiest way for me to turn this filter into a high-pass filter? Do you have a question or answer? Give me the question.
Well, the question kind of follows later. So I guess my answer would be to use negative value for omega. I mean alpha.
Alpha. So all you have to do is, if you have a design parameter or a knob on your box, and you can turn that knob so this alpha moves between -1 and 1, to make this high pass, all you have to do is take this alpha to the other side. Okay? And in that case, the shortest length of the red vector will be when you're at pi. The longest length will be when you're at 0. Now, what's your question?
And then there was no restriction on alpha other than that it's magnitude less than 1, right?
Right.
So then can we put it as sort of like I over 2, then we would sort of change the position of the height, the peak of the graph, right?
So as long as I insist that alpha is a real valued parameter, and that it's positive between 0 and 1, I get a low-pass filter. If it's negative, so let's put this down. Alpha between 0 and 1, we get a low-pass filter. Alpha between 0 and -1, you get a high-pass filter. Now the question is, I only impose the constraint on alpha that it be less than 1. In other words, strictly inside the unit circle. Well, what if it's not real valued and it's roaming about somewhere inside the unit circle? What if I put alpha along the imaginary axis? Then where would the peak occur? Pi over 2. If I put it on the negative side of the imaginary axis, it would peak at 3 pi over 2 or minus pi over 2. And if I put it at arbitrary locations here, it would peak at the angle corresponding to where I've placed the x. So this is all very good. That's exactly the kind of thinking I want you to do. This is what's called design-oriented analysis. So you're given the form of the equation. You only have one parameter alpha to play around with. And by placing that alpha in different locations, you can create different types of filters. Now, one thing to be said about an alpha that's not on the real axis is that it turns your filter into a complex filter, because your impulse response now will be complex value. Remember, h of n is alpha to the n u of n for this filter. So if alpha is complex valued, then filter is a complex filter. Complex filters have some applications in advanced signal processing. They're somewhat beyond the applications of this course. But one of the things I will do after this example is to introduce a filter that has more than one of these x's. And it turns out that if you design a filter with one of these x's somewhere up here, and also place an x where they're at the complex conjugate location, you're always guaranteed to have a real valued filter. We'll do that. So if I want to have, so your solution to creating a bandpass filter, let's say that peaks at pi over 2, if alpha is, let's say, let's do 3i over 4. This one was at 3 over 4. Let's put alpha at 3i over 4. On the circle, you'd have an x here, 3/4 I. And your e to the I omega would be on the unit circle. Your red vector would be from the x to the e to the I omega point. And as this particle moves around the unit circle, this red vector has minimum length at pi over 2. So when you plot the magnitude response, you'll get, this is 0, this is pi over 2. Let's see. Whoops. and its minimum is at minus pi over 2. Yeah, okay. So minus pi over 2, it says its minimum, and then it starts rising again. This is pi over 2. The problem with this is that your impulse response will be complex valued. Implementing it is more complicated. So we say, what if we want a real filter, or real valued filter, that peaks at pi over 2? Now you can start with the diagram and work your way back to the equation, the difference equation. Remember, the difference equation is what gives you the block diagram. And the block diagram is what you actually code into a computer. That's how you implement the filter in MATLAB, LabVIEW, whatever. Okay? So now I want an x here and an x here. 3/4 I and minus 3/4 I. And I have an e to the I omega here. I put both of these in the denominator. So what would be the frequency response? One over e to the I omega minus 3/4 I times e to the I omega plus 3/4 I. I made a point about this filter having a frequency response that's of the form of a polynomial in e to the I omega over a polynomial in e to the I omega. In high school, you guys studied ratios of polynomials, or if not that, then certainly in your calculus class. A function that's of the form px over q of x, where x is a variable. This is like your algebra, high school algebra type of variable. Polynomial in x, polynomial in x. These functions are called rational functions of x. Rational functions of x. Anytime you have an LTI system that's representable by a linear constant coefficient difference equation, its frequency response is going to be rational in e to the I omega. So any discrete time LTI system representable by an LCCDE has a frequency response that is rational in e to the I omega. And just going through the process that we use to derive this one, you can easily see how this will generalize to more complicated difference equations. So here I have the same story. I have a polynomial which is 0th order in e to the I omega in the top. And I have a polynomial that is 2nd order in e to the I omega in the bottom. Instead of x squared, x cubed, and so on, I have e to the I omega squared. See what I mean? It's just a polynomial in e to the I omega. So the magnitude response of this filter will be what? I'll give you a break right after this. What's the magnitude response? What's the numerator? 1 over magnitude of that product. What's the magnitude of a product? Product of the magnitude. So I have the product of one of those red vectors' lengths and the product of the other vector's length. Plus, yeah, thank you. Okay. Now, it's not always easy to see from the diagram what this is going to look like. But this thing is going to have 2 humps. Roughly. The closer I make alpha go to the unit circle, the closer these peaks are to pi over 2 and minus pi over 2. When you go to, you can see that as you go to the second order, it's not as straightforward to plot these peaks. But roughly speaking, crudely speaking, you get a peak when you get close to one of the x's, and you get a peak when you get close to the other one of the x's. Let's take a break, and we'll continue with this story. We're doing design. We're doing design-oriented analysis. We're studying these filters with design in mind. How do you perturb or change something about the filter to get a different type of filter? And notice, oh, the one thing I forgot. Why did I put these in complex conjugate forms? When you multiply it out, you get what kind of a polynomial in e to the I omega? What are all the coefficients? All the coefficients are real. And so when you write out the difference equation, which we'll do after the break, you'll see all the coefficients are real valued. And so you have a real valued filter. All right, folks. Yeah. That's because I know things that you know not. If it makes you feel better, I'll put an e to the I 2 omega here. And let's do that, actually. The point is, I want something whose magnitude is 1 in the numerator. So I'll put that in. And let's see what the difference equation for this system looks like. One thing I should point out is that the farther away these two x's move from the unit circle, the more inaccurate this plot will be. Okay? When, instead of 3/4, if I had picked 0.99 I, that means this x is pretty darn close to the unit circle. Then when you look at the denominator, so I have h of omega. So let h of omega be e to the I 2 omega. Instead of 3/4, let's say I have e to the I omega minus 0.99 I, and e to the I omega plus 0.99 I. Okay? Now, I'm pretty darn close to the unit circle when this e to the I omega, well, these two will be pretty darn close to the unit circle. So e to the I omega now comes all the way up here. So omega is pi over 2. In the denominator of the magnitude response, you have the magnitude of the numerator, which is 1, times the magnitude of each of these terms. If I am at pi over 2, which one of these magnitudes is going to dominate the value of this ratio? The shorter one or the larger one? The shorter one, because that's going to be tiny. 0.01 in the denominator, I'll have a 0.01 times a number that's pretty close to 2. Right? What do I get? 1 over at omega equals pi over 2, the magnitude is approximately 1 in the numerator divided by, what's this one? 0.01 times about 2. Okay, it's just under 2, but about 2. So this 0.01 is going to dominate. And what kind of a behavior are you going to see in the frequency response at pi over 2? Sharp peak. Okay? So you get 1 over 0.02, which is what, 50? And the same story when you go down here. As these x's move away from the unit circle, the nonlinear multiplicative effect of these two magnitudes in the denominator makes it more difficult to determine where the peak is exactly, at least visually. So those peaks won't be exactly at pi over 2 and minus pi over 2. They'll be roughly in that neighborhood. But the point is you get peaks in the mid-band range. It'll be a bandpass filter. Going back to the original filter, how do I get better peaking or stronger or sharper peaking at 0? What do I do to that alpha? Closer to what? Closer to the unit circle. Because if I move alpha closer to the unit circle, when omega is 0, the length of that red vector will be very tiny. The inverse of that will be very large. And as I move away from 0, it decays very fast. So these are the kinds of geometric reasonings that I want you to get used to doing to either save yourselves a lot of work analytically, or making sure that whatever equations or expressions you find is consistent with your geometric intuition or expectation how the filter behaves. That kind of a skill is very important. It's the kind of back of the envelope calculation that I want you to get used to. Now let's see what the difference equation is that represents this filter. How do I find it? Here, to find the magnitude response, I multiply top and bottom by a sufficiently large power of omega to get rid of all the negative powers of e to the I omega. So what do I do there to get a difference equation with only delays in it? Actually, we're prepared to write this as h omega is e to the I 2 omega over e to the I omega minus alpha and e to the I omega minus alpha star. Right? That's essentially what that filter is. And you pick your alpha. What's the denominator polynomial in e to the I omega? You all know how to do x minus alpha times x minus alpha star, right? I hope. What do you get? X squared minus what? Minus alpha star x minus alpha x. So it's minus alpha plus alpha star x. And what's the last term? Magnitude squared. Alpha times alpha star is magnitude alpha squared. Minus times minus is plus. So what do you get when you add alpha and its conjugate? Minus 2 times the real part of alpha x plus alpha squared. Notice all the coefficients are real. So instead of x here, I have e to the I omega. This x is not the input. This x is your algebra, run-of-the-mill high school algebra variable. So instead of x, I have e to the I omega. So in the denominator here, I have x squared. So I have e to the I omega squared, which is e to the I 2 omega, minus twice the real part of alpha times e to the I omega plus alpha squared. That's my filter. What is alpha in this case? Purely imaginary. Right? So what happens to the middle term? Zero. So when alpha is 3/4 I, you get real alpha equals 0. And now I can write the frequency response in a slightly more amenable way, amenable to converting to a difference equation. So I have h of omega equals e to the I 2 omega over e to the I 2 omega minus magnitude squared, 9 over 16. Plus, sorry. I multiply top and bottom by this negative power. So I get a 1. I get 1 plus 9 over 16 e to the minus I 2 omega. And can you do some pattern matching and tell me what difference equation this corresponds to? Pattern match with the other difference equation and see how we got h of omega. Why don't you talk to your neighbors and see what you come up with? Okay, so answering this question requires some bravery because we don't exactly have the concrete tools to find the answer. That's why I asked you to pattern match and see what we did in the previous case, in this case, and see what you get in this case. So here, let me just group the terms for you and just to give you a better idea. I have 1 plus 9 over 16 e to the minus I 2 omega. The whole thing is multiplying h is equal to 1. Over here, what did you have? 1 minus alpha e to the minus I omega h equals 1. So what's the difference equation? Meatball.
I'm looking at this and I'm seeing drawn blanks. It looks to me like we're multiplying by conjugate, but I haven't been able to work it out.
Let me rewrite this equation under this one and see if you see what I mean. Here I have y of n minus alpha y of n minus 1 is equal to x of n. Notice a delay by one sample corresponds to an e to the minus I omega. Alpha, alpha. No delay, y of n. So can you tell me what this is? Yeah, so what's the first term? Y of n. Then what? Did I? Yeah. Well, it's not a minus, it's opposite sign of that. I have a plus here. Plus, this is actually magnitude alpha squared. So it's 9 over 16. This is plus magnitude alpha squared. Y of n minus 2 equals x of n. That's your equation. That's the difference equation. And if you don't believe me, plug in x of n equals e to the I omega n in this equation, and I bet you're going to get the same thing. That's how I can make problems right on the spot at the blackboard. Plug in. If you don't believe, verify. Trust me, but verify. Here we go. Let x be that. Y of n will be h times e to the I omega n. Plug it in there and you'll get the same thing. So the equation that gives that filter is this one. This would correspond to h of omega equals 1 over e to the, no, what did we have? Gives e to the 2 omega e to the I 2 omega plus alpha squared, which I can write as 1 over 1 plus alpha squared e to the minus I 2 omega. These two correspond to each other. I did some gymnastics in going from here to here. You can verify the answer by plugging in x of n equals the complex exponential, y of n equals h times that complex exponential, and verify that this is the answer. Can you draw the block diagram for this? Now you want to implement it on the computer. You want to program it in. So you want to know how many storage elements you need and what you need to do. How many delays do you need? 2. So do it. Give me a delay adder gain block diagram for this filter. Okay, what do we got? Well, you answered the previous question, so pick somebody else.
How about blue shirt in the row behind me, kind of in the middle?
Blue shirt.
And back again.
Zach.
Alright, so I started off with just the, I started off the line going from X to then all the way over to Y then. And then near the Y then, and I had a line going down into the delay block. And then I multiplied after that by magnitude alpha.
How many delays do I need?
Well, I did delay then alpha again. I guess you could do delay twice and then multiply by magnitude alpha squared. And then take it back in.
Which one's minus? This one or this one? Well, rewrite the difference equation. You're going to get y of n equals y at n equals y of n minus 2 times alpha squared minus here, plus there. Okay? So going from the frequency response to the block diagram is something that you're still shaky on, and there's a reason for it. We haven't covered the necessary theoretical ground for you to do that. But certainly going from the difference equation to the frequency response and the delay adder gain block diagram is something you should be able to do by now. Let me give you another example just to see how comfortable you are with this graphical method. here's my filter, described by this difference equation. Find its frequency response. And from there, find its magnitude response. How are we doing with the frequency response? Go for it.
So you first substituted x equals omega and y band equals h of omega times e to I u, or I omega.
Yep, we use our standard procedure. If x is the complex exponential, y is h times the complex exponential. And when you plug it in and you get to the answer, what do you get?
H omega equals 1 minus e to the negative I omega over 1 minus 0.99 e to the negative I omega.
Did you get this? Very good. Now, to find the magnitude response, I'll do this part myself because we're running out of time. To find the magnitude response, I first multiply the numerator and denominator by the power I need to get rid of all the negative powers. And what's that? E to the I omega. So in the numerator, I'll have e to the I omega minus 1. And in the denominator, I have e to the I omega minus 0.99. Okay? So when I draw this on the unit circle, I have e to the I omega sitting somewhere on the unit circle. Okay? I have a 1 in the numerator. I'll designate that with a hollow circle. That's 1. So there's an e to the I omega minus 1. It's the length of that blue vector. And I have a 0.99 in the denominator. I represent that with an x. That's 0.99. Where's my red chalk? And the length of that is this vector right here. Okay? Now, there's a reason I've picked 0.99 for this question. H of omega magnitude is the ratio of the magnitude of the blue vector over the red vector. when I'm sufficiently distant from omega equals 0, what can you tell me about these two? They're almost equal, right? So is 1 approximately for omega sufficiently, actually instead of writing it this way, let me just plot it. So 0 here. If I'm sufficiently distant from 0, this magnitude response is 1. What happens at 0? Omega goes to 0. The denominator is finite, small but finite. And the numerator is what? This is a very neat filter. It's called a notch filter. And it passes everything, but yanks out DC, and frequency is very close to DC. If you want this to be sharper, you make the 0.99 even closer to the unit circle. Go away.